We are back with the chapter Algebraic Structures. Today we are going to study some of the topics. The first one, addition modulo, multiplication modulo, and examples based on that. And last, permutation group. First, let's understand what is addition modulo. It is written as A plus M, that means A plus subscript M B, or also bracket of A plus B modulo N. It is defined as A plus subscript N B equals to R, where R is in between 0 and M. Where A and B both are integers, it can be positive or negative, and M is strictly a positive integer. And R is the least non-negative remainder when the ordinary sum of A and B, that means A plus B, is divided by M. For example, here 14 addition modulo 6 8, that means what we need to do, just add 14 and 8, that is 22. It is also written like this, 22 percentage 6, that means 14 plus 8, that is 22, divide by 6. So the remainder will be 4. In same manner, 9 addition modulo 5 3, that means add 9 plus 3, add 9 and 3, that is 12. 12 percentage 5, that means 12 divided by 5, so we'll get remainder 2. Same way, if it is negative number, so minus 23 addition modulo 3 3, that is minus 20 percentage 3, so the remainder will be 1, as 7 into minus 3, it is 21, plus 1, so it is the remainder is 1. Next, in same manner, multiplication modulo P, it is written as A cross P, that is multiplication subscript P and B. It is defined as R, where R is in between 0 and P, where A and B both are integers and M is a positive integer. Here there is no restriction for positive and negativity of A and B, but M is strictly a positive integer. R is least non-negative remainder when the ordinary product of A and B, that means A into B, is divided by M. For example, 8 multiplication modulo 5 and 3. So that means first we need to multiply 8 and 3, that is 24, and 24 divided by 5. So that is the remainder will be 4. Same way, 4 multiplication modulo 7 2. So that is 4 into 2, that is 8, and 8 divided by 7, we get remainder 1. Are we clear? Now let's take one example. Let G equals to, here G is the set, that is 0 1 2 3 4 5, and prove that G plus 6 is an abelian group. That means plus 6, that means the operation is plus 6, that is addition modulo 6, and it is an abelian group. So to prove the abelian group, we need to check all those 5 axioms or conditions. That means the first one, closure property, associative property. Third, existence of identity, existence of inverse, and the last one, commutativity. So first, for all these 6 elements, we need to construct a composition table. So that would be like this. Here, plus 6, that means addition modulo 6, 0 to 5, 0 to 5. Now, this first row and first column will be same as it is. Why? Because 0 plus 0, that is 0, and 0 divided by 6, the remainder, that is 0. Same way, 0 plus 1, that is 1, 1 divided by 6, that is 1. So all these entries will be same. Now in the second row, 1 plus 4, that is 5, so 5 divided by 6, 5. Now 1 plus 5, 6, 6 divided by 6, so remainder is 0. Now same way in the third row, 2 and 4, consider 2 and 4. So 2 plus 4, that is 6, and 6 divided by 6, 0. Now 2 plus 5, that is 7, 7 divided by 6, the remainder is 1. Same way, consider this 4, 4 plus 4, that is 8. 8 divided by 6, that is remainder is 2. Same way, 4 plus 5, 8, sorry, 9. 9 plus 9 divided by 6, so remainder is 3. So same manner you can put all the entries like this. Now first check the closure property. Here you can check that all these entries belongs to this G 0 to 5. Okay, it, other than these entries there are no other entries. First, so closure, here all the entries in the composition table are the elements of the G, so it is obvious in most of the cases of closure will be obvious. Hence G is closed with respect to addition modulo 6, that is plus 6. The second property, associativity or associative property. For that, what we need to check, for every ABC in the G, in the set G, we need to check this condition. That means A plus 6 bracket of B addition modulo 6 C equals to same as this. So let us consider one example. This is also true. Now let A equals to 1, 2, 3. Then we need to prove this both has to be same. So now first consider this. Now 2 addition modulo 6 and 3. So that is 5. 5 divided by 6. So remainder will be 5. Now 1 plus 5, that is 6. 6 divided by 6. So remainder will be 0. Here the answer will be 0. Now consider the right hand side. Now 1 plus 2, that is 3. 3 divided by 6. So here it is 3 and this is the same. Now 6 divided by 6, so 0. So both answers are 0. Similarly, you can check for any numbers, it will be same. Hence it is associative or associativity is there. Hence plus 6 is associative. Next, the third one, existence of identity. What will be the identity? Here 0 is the identity element, as for any element we can see that 0 plus 6 or and A, it will be A. For example, 0 plus 6, 0, that is 0. 0 plus 6, 2, that is 2, and so on. You can check for any entries. Hence 0 is the identity element. Now fourth, existence of inverse. For this, for every A belongs to G, there must be B belongs to the set such that this holds. That is A plus 6, B equals to 0. That means for every A there has to be B such that it is the identity element. Here identity element is 0, so we have written here 0. Now from the table, the inverse of 0 is 0 as this. Same way, inverse of 1 is 5 as the addition modulo 6 is 0. How? Let us consider the table here. Now here consider the rows. Whenever there is 0, here inverse of 0 is 0. Here 0 is now inverse of 1 is 5. Now 0 is here, so inverse of 2 is 4. Here 0 is, so inverse of 3 is 3. 0, so inverse of 4 is 2, and here inverse of 5 is 1. So okay, same way. So the existence of inverse, so inverse exists for each and every element. Last, commutative. It is obvious, it is commutative as the corresponding rows and columns are identical, same, so that means it is commutative. Hence all the 5 axioms are satisfied. Hence G plus 6 or G addition modulo 6 is an abelian group. Let us consider another example for multiplication modulo 7. Prove that just G, here it is given as 1 to 6, is a finite abelian group of order 6. Of order 6, that means here there are 6 elements, so it is called of order 6 with respect to multiplication modulo 7. Okay, again we need to construct table, composition table like this. Here multiplication modulo 7, the entries are 1 to 6, that means 1 to 6, 1 to 6. Now first, same manner as we did previously, 1 to 6, all the entries will be same. Now consider this. Now 2, what we need to do, this is multiplication modulo 7, that means 2 into 2, that is 4. Now 4 divided by 7, the remainder will be 4. Same way 2 into 3, that is 6, 6 by 7, the remainder is 6. So from here the entries will be changed. Now 2 into 4, that is 8. Now 8 divided by 7, the remainder is 1. 2 into 5, that is 10. 10 divided by 7, the remainder is 3. 2 into 6, 12. 12 divided by 7, the remainder is 5. Now from here 3 into 3, that is 9. 9 divided by 7, that is the remainder is 2. Now 3 into 4, 12. 12 divided by 7, the remainder is 5. 3 into 5, 15. 15 divided by 7, so remainder is 1. And similarly we can construct all these entries. Now first property, closure. Consider here you can check all the entries are from 1 to 6, that means all the entries are from the given set 1 to 6. So closure is obviously it is there. Closure, all the entries in the composition table are elements of the set G. Hence G is closed with respect to multiplication modulo 7, that is x7. Now second, associativity. Here what we need to check, for every ABC belongs to the set G, this property has to be followed. Now A cross 7, B cross 7 and C equals to this. Let's consider one example. Let A equals to 4, 5, 6. Let A, B, C equals to 4, 5, 6. So that means we need to check this property, that is 4 multiplication modulo 7 bracket of 5 multiplication modulo 7 and 6. So first consider this. So 5, so what is the answer? 5 into 6, that is 30. 30 divided by 7, so what will be the remainder? 2. So here the entries is 4, x7, 2. Consider this, 5 into 4, that is 20. 20 divided by 7, so remainder will be 6. Okay, and 6. Now here 4 into 2, 8. 8 divided by 7, so the remainder will be 1. And here 6 into 6, 36. 36 divided by 7, so remainder will be 1. So for you can check for any entries, the associative will be there, so hence it is associative. Next, existence of identity. Here what will the identity? In the previous example 0 was the identity. Now here 1 is the identity element for any element, as here please correct it, it is 1, as 1 x7 2 equals to 2. Now 1 multiplication modulo 7 is multiplication modulo 7, 6 equals to 6, and you can check for the rest of the numbers, everything will be true. Hence once 1 is the identity element. Now existence of inverse. So that means for every A belongs to G, there must be B in the given set such that what we need to check, A multiplication modulo 7, B equals to the identity. Here identity element is 1, so 1 is returned. From the table, for example, the inverse of 3 is 5. How? Let's consider the table. Okay, here whenever the entry 1, here 1 is there, so inverse of 1 is 1. Here identity element is 1, so inverse of 2 is 4. Here 1, so inverse of 3 is 5. Here 4. Here 4, so here 1 is there, so inverse of 4 is 2. Now here 1, so inverse of 5 is 3. Here 1 is there, so inverse of 6 is 6. So you can check. Okay, here jo inverse of 3 is 5, the same way inverse of 5 is 3. Inverse of 1 is 1, inverse of 2 is 4, so inverse of 4 is 2, inverse of 6 is 6, and so on. So So we get inverse of all the numbers in G. Now commutativity, it is obvious. It is commutative as the corresponding rows and columns are identical. Here all the 5 axioms are satisfied. So hence G multiplication modulo 7 is an abelian group. Okay, next, some properties of groups that we should know. The first one, identity element is unique. See, whatever the examples we did, you can see that the identity element is unique. In the previous example, one was the identity and it was unique. Second, inverse element is also unique. Inverse element for each and every element is unique. So, third, if inverse of A is B, then inverse of B is A. Like if inverse of A is A inverse, then A inverse of inverse, that is A. Okay. Now next, permutation. Suppose S is a non-empty finite set having n distinct elements. Then a 1 1 on 2 function, that means a bijective function from S to S, is called permutation of degree n. Note, so there exist n factorial distinct permutations from S to S. That means if we have 3 numbers or 3 degree, or okay, then there will be 3 factorial, that means 6 distinct permutations from the given set to itself. Now, set of all permutation is known as permutation set, and it is denoted by capital P subscript n. Now, permutation group, it is clear that a group defined by permutation, that is a permutation group. But definition, let us consider a definition. If Pn is the set of permutations and composition function is a composition defined on a set S, then Pn forms a group and it is known as a permutation group. Next, see the notation. If there is a set x1, x2 up to xn and sigma is a permutation, then it can be described or it can be represented as like this. Sigma is here x1, x2, x3 and so on xn, and this entry, that means sigma of x1, like function of x1. Here sigma is the function, so sigma of x1, x2. So this entry will be sigma of x2, here x3. That means this entry will be sigma of x3 and so on. Now if we want to define composition, it is easy. Suppose we have two functions f and g. Here a1's image, that means sigma of a1 or f of a1 equals to b1, f of a2 equals to b2 and so on. So directly it is written as a1 equals to b1, a2 goes to b2 and so on, an goes to bn, and here b1 goes to c1, b2 goes to c2 and so on. Now if we want to find composition fg, then first consider a1. Now a1 goes to b1. Now in g, b1 goes to where? c1. So for this consider a1 and for this consider c1. That means the entry will be a1 goes to c1. In similar manner, a2's image or a2 goes to b2 and here b2 goes to c2. So what will be the entries? a2 and c2 and so on. So composition is good. Now identity permutation. From the name it is very clear. If every element of the set maps to itself, then it is called identity permutation. That means 1 goes to 1, 2 goes to 2, 3 goes to 3 and so on. Now next, cycle notation. Now consider this permutation. There are 3 entries, 1, 2, 3 and 3 images obviously. Now 1 goes to 1, so 1 goes to 1, that means 1 goes to itself. Here 2 goes to 3 and 3 goes to 2, that means one cycle is completed. So this can be denoted by like this, cycle 2 3. And why we have not returned 1? Because it goes to itself, so that can be neglected. So this permutation can be defined or denoted by like this, only this, cycle of 2 3. That means 1 goes to itself and 2 goes to 3 and 3 goes to 1. Let us consider another example. See, consider this permutation. you have 7 entries. So how to write this? Now suppose first consider this. 1 goes to 4. Now 4 goes to 5. Now 5 goes to 1. So one cycle is completed. Again 1 goes to 4, 4 goes to 5, and 5 goes to 1. And again 1 goes to 4. So one cycle is completed. So this entry can be described as this. Sorry, 1 4 5. That means 1 goes to 4, 4 goes to 5, and 5 goes to 1. So one cycle is completed. Now consider 2. So 2 goes to 2. So simply write this 2. Now consider 3. 3 goes to 7, 7 goes to 3, and 3 goes to 7. So again one cycle is completed. So that means 3 and 7. Simply write bracket of 3 and 7. And which entry is left? 6 6. So, and 6 goes to 6 itself. So 6. Now this can be written in very similar way or simpler way, like this. Neglect 2 and 6 because they goes to itself. So 1 4 5 3 7. That means from this we should be able to write this permutation. How? Here 1 goes to 5, one's image is 4, 4's image is 5, and 5's image is 1. 3 goes to 7, 7 goes to 3, and the rest of the entries goes to itself. Let us consider the last example here. Let S equals to 1 2 3. Then P3 is a set of all distinct 1 1 onto functions from S onto itself. That is, P3 is defined as this set of all functions such that F is a permutation of degree 3. Show that P3 is a permutation with respect to composition of function. Okay, it is a permutation group, sorry. Show that P3 is a permutation group with respect to composition of function. Here, degree of P3. Here, degree of P3 is 3. So that means we will have 6 distinct permutations. So that means 3 factorial, that is 6. So hence there will be 6 distinct permutations. And what are they? So P3, the set will be like this. There are 6 permutations. The upper entries will be same 1 2 3 1 2 3. Now 1 2 3, what is the permutation of 1 2 3? So there are 6 possible entries: 1 2 3, 1 3 2, 2 1 3, 2 3 1, 3 1 2, and 3 2 1. So these are all possible 6 entries. Now let us rename it. First I. So this is the identity permutation. 1 goes to 1, 2 goes to 2, 3 goes to 3, and the rest of the entries or rest of the permutations we are naming as f1 f2 f3 f4 and f5. So there are total 6 permutations. Now there is a composition function. That means the operation is composition. First calculate f1 and f2. How to calculate? So consider this f1 f2. 1 goes to 1, 1 goes to 2. Entry will be 1 2. 2 goes to 3, 3 goes to 3. So entry will be 2 3. Now 3 goes to 2 and 2 goes to 1. So 3 1. But this is same as f3. So f1 f2 is same as f3. In same manner we have to calculate all the entries. That means f1 f2 f2 f3 f3 f4 f4 f5. So there will be, so this will be the table. This is the composition I f1 f2 f6, sorry, f1 to f5, I f1 to f5. Now this is I into I. Now I into f1, that means identity into f1, identity composition f1. So this will be same f1 to f5, same way f1 to f5. Now consider this f1 f1, that is I. Now f1 f2 we have already calculated, that is f3. F1 and f3, let's consider f1 and f3. Here f1 and f3. Now 1 goes to 1, 1 goes to 2. So that means what we'll get 1 2. Same way 2 goes to 3, 3 goes to 1. So 2 1. 3 goes to 2, 2 goes to 3. So that is 3 3. So that is nothing but f2. So f1 and f3, that is f2. In similar manner we can calculate all these entries. Okay, now we need to check it is a group. It is a group. So that means all the four axioms has to be followed. The first one, the closure property. That means here you can see that all the entries are from the given set, that is this, that is I, f1, f2, f3 and f4. So it is there. So closure is there. The second one, associativity. You can check for any three numbers, consider f1, f2 and f3 and it will hold. And so associative is there. The third one is existence of identity. Here what will the identity element? It is very obvious, I is this 1 1 2 2 3 3. So identity is there. Okay. And the last property, existence of inverse. So that means for f1 there has to be some element such that f1 composition something is I. So let us consider this table. Here where is I. So that means inverse of I is I. That is obvious. Now f1's inverse is f1 itself. So here entry is I. So we can say that f1's inverse is f1. Here the entry is I. So that means f2's inverse is f2. Now here the entry is I. So f3's inverse is f4. Same way f4's inverse is f3 because the entry here it is I. Now f5's inverse is f5 because the entry is I. Hence we get inverse of all the entries. Hence all the four axioms are satisfied. Hence it is a group. Hence it is a group under which uh, operation, the composition. Okay, thank you.